Now we study the composite function. Let's consider that f is a function from set A to B and g is another function from set B to C. Okay, then the composite function denoted by GOF, that is called as g of f, and it is defined from the set A to C, is called as the composite function, where g of f of x means that it is the g of f of x. So it's like there is a hierarchy of functions. Now let's understand this graphically. Suppose this is the first set A, this is the second set B, and this is the third set C. Now from first set to second set we have the function f, right? And from second set to third set we have the function g, right? So that means if we denote x as some element in the original set, okay, so its image under the function f will be nothing but f of x, right? Now when that image goes in as an input to the second function, that is g, so what we get at the end is nothing but g of f of x, isn't it? It's clear from the terminology of image and pre-image. So it means that from x to the last value, that is g of f of x, this particular function from A to C is nothing but the composite function of f and g, right? So let us see some of the important properties related with a composite function. Composition of two functions is not necessarily commutative, but it is associative. So by commutative we mean f of g is not necessarily same as g of f. Okay, it may be same, but it may not be same also. So in general we say that it's not commutative. However, the associative law is true for the composite functions. So that is, if we associate g and h as two functions first in the composition and then we associate with f, then that is equivalent to associating f and g first and then taking its composite with the function h. Okay, so therefore the associative law is true for composite functions. Now the second property is, if f and g both are 1-1 functions, then g of f is also a 1-1 function. And third property is very much similar, that is, if f and g are onto, then g of f is also onto. So let us just visually confirm this particular property. Suppose the first function is something like this. The first set consists of 1, 2, 3. Okay, the second set consists of 2, 4, 6, right? And the third set consists of something like, say, 4, 16 and 36. Alright, so now we observe that both the functions which are f and g, they both are 1-1. Alright, so therefore if we travel from 1 with a path till we reach the set C, so therefore here the first path is from 1 to 2 and then from 2 it leads to 4. So that means from 1 we ultimately reach to 4, which is a unique image. Alright, now similarly 2 will also lead us to value 16 and 3 will also lead us to value 36. So that means there are no two elements in the first set A which have the same image in set C. Alright, so therefore we see that the composite function of g of f is also a 1-1 function, right? Similarly we can also confirm that the composite function is onto if the two individual functions are also onto. Okay, so let us move to the next properties of composite functions. Now the fourth property is, if g of f is 1-1, then f is also 1-1, but g is not necessarily 1-1. Alright, so now here we see that g of f is 1-1, then it means that f is also 1 1, and by f we mean it is a function which is written afterwards, but in actual sequence it comes first. So let us see one example, that is, so here are our three sets, we call them as A, B and C. Right. Let's consider here the function f as 1 2 3 as shown here. Right. Now function C may be something like this. Sorry, the second function is G. Now it may be drawn something like this. If you observe, if we consider the composite function from A to C, it will be definitely a 1 1 function, because each element in the first set will lead us to a value in the last set. Alright, so there are no two elements in the first set which lead to the same value. We can literally trace the paths and confirm this. Alright, so that means the composite function g of f is 1 1. This is the example we are taking. Now as per the property, it means that the first function also has to be necessarily 1 1 if the composite function is 1 1, whereas the second function, that is a function which comes later in the sequence, need not necessarily be 1 1. So here we see that the function g is not 1 1, because we observe that the two elements 3 and 4 in set B have the same image in set C. So therefore g is not 1 1. Alright, but f has to be 1 1. Now if you want to invalidate this, it may happen that, for example, suppose we add one element in first set, and let us consider that this also gets mapped to the value 3. Then what will happen is, in the first set both of the values 3 and 4 will get mapped to the value 3 in the composite function. So then it won't be a 1 1 function. Therefore it violates the given property. So therefore the property is true. And similarly we can also verify the fifth property, that is given as if g of f is onto function, then g also has to be an onto function, but f is not necessarily onto. Alright, so now here it is in the opposite sequence, that is g of f is onto, then g is onto, and g means it's the second function in the sequence, that also has to be an onto function. But the previous function, which is f, that need not necessarily be onto. Alright, now let's go ahead and solve few questions based on this. If f is a function defined from reals to reals and given by f of x equal to 2x minus 1, and g is another function from reals to reals and it is given by g of x equal to x square, then find the value of g of f of 3. Right. So first of all, let us understand what does the composite function means. So we know that g of f is nothing but g of f of x. So now in place of f of x, we can write its expression, that is 2x minus 1, because we know that f of x is given by 2x minus 1 as per the definition. Now moving ahead, if we see the definition of g of x is equal to x square. So whatever comes in as an input to g, the output is the square of that. So therefore if we have g of 2x minus 1, the result will be nothing but 2x minus 1 the whole square. Right. So that's the general expression for g of f. So therefore if you want to find the value of g of f at a specific point, say x equal to 3, then we'll merely substitute x equal to 3. So therefore it's nothing but 2 into 3 minus 1 the whole square, which is nothing but 2 into 3 is 6 minus 1 is 5 and 5 square is 25. So that's the answer, right? Let's see one more question. If f of x is given as, now this bracket x means it's the greatest integer function, and g of x is the modulus function, that is mod x, then evaluate the value of g of f of minus 5 by 3 minus f of g of minus 5 by 3. So this basically means g of f of minus 5 by 3 minus f of g of minus 5 by 3, correct? So we have to now think and substitute the corresponding values. So that is g of. Now let's see what is this, that is f of minus 5 by 3. We know that f is the greatest integer function. So we have to find what is the greatest integer less than or equal to minus 5 by 3. Now if you see, minus 5 by 3 is nothing but, if we divide 5 by 3 we will get 1.666 and so on recurring, alright. So therefore obviously the greatest integer which is less than or equal to this particular number is nothing but minus 2, isn't it? So therefore the answer of this f of minus 5 by 3 is minus 2, minus f of. Now in the second bracket here we have g of minus 5 by 3, and what is g? G is the modulus function, that is absolute value. So absolute value of minus 5 by 3 is nothing but obviously plus 5 by 3, alright. So going ahead, now we have to evaluate g of minus 2, that means absolute value of minus 2 which is 2, and minus, now f of 5 by 3, that is the greatest integer less than or equal to 5 by 3, and 5 by 3 is, we just saw that it is 1.6666. So the greatest integer less than or equal to this particular number is nothing but 1. So hence the final answer is 2 minus 1, which is 1.